Okay, so good evening all. So as see before going for the today lecture, which is basically on a sample storage preparations, sample preparation, and then we'll discuss something on the separation science, and then we'll the chromatography, which is a part of the separation science only. See, as I told you, basically these lectures basically need maybe about say 100 lectures, which I am supposed to cover in these 6 lectures. So all these lectures meant for just giving a idea how you can carry out the various kind of analysis. And suppose if you had come across of any problem during your research and developments or during your study, so how to approach basically an analytical chemist to resolve your problems. Okay, so this basically I prepared for Mr. Singh. I think I is not there so far. So once he will join it, I will explain what is the difference between the reference material, certified reference material, and the standard reference material. So, see, basically, during this 6 course of lectures, always I will take some time for doing the recap. See, in the first lecture, what we had covered, the analytical terminology, and the analytical terminology, see, we have started for the what is sample, and then sample matrix, analyte, standard solutions. Then we have covered the PPM, PPT, calibration curve, sensitivity. I think Sarjan Singh had come. Okay, Sarjan, is there no? Sarjan Singh, this is basically PowerPoint I prepared for your answer. So I had very critically, it is written in this PowerPoint what is the difference between the reference material, then CRM and SRM. As I told you, that SRM basically meant for, it is a patented. Basically, there is no difference between the CRM and SRM. But SRM, this is a term basically, patented by the by the US. The term standard reference material is registered with the United States Patent and Trademark Office. So this is basically used by the NIST only. And then there is one more terminology nowadays people are using, that is the Mistressable reference material, that is NTRMTM. And see, reference material basically is a generic term used for material sufficiently homogeneous. And this material, whatever the material you are getting for preparing your standard solution for the calibrations, this is basically comes in that category of the RM. And if your lab is having got this ISO 3435, it means that you have been externally accredited by a reputed agency and in the field of the preparation of this reference material, then it is called as a certified reference material. The reference material coming from that lab is termed as a certified reference material. And if this lab is belongs to this NIST, that is the US concern, then this is called as a standard reference material. So standard reference material is basically patented by the in the United States. Okay. Now this we start with the recap. That is the analytical terminology. See, analytical terminology we had covered first the sample. What is sample is there, and then how this analyte matrix, and then we cover the various kind of concentrations, whether what is mean by ppm, ppb, and we had seen that how to define the solutions and molarity, normality, and calibration curve, and the sensitivity of the instrument. Sensitivity of the instrument is nothing but the slope of the calibration curve which you had particularly come out from that instrument, whether it's a ICP-OS or whether it's a GFAS or FAS, even spectrophotometers, any equipment actually. So the calibration curve of that gives the sensitivity of the instrument. Then we had come across the various kind of, we had discussed the type of analytical techniques. See, the various analytical techniques has basically distributed in the absolute, relative, and the comparative techniques. Absolute techniques which does not need any kind of a reference materials. Okay, so they does not need any support, or they are on. See, you carried out some chemistry and get out the results of that thing. So basically, best example of this is the gravimetry, and these are the technique. Whenever we need an RSD value, that is the relative standard deviation less than a 1%, it is always been suggested that one has to carry the absolute techniques only. But absolute techniques having its own limitations are there. Then we discuss about the relative methods. See, all the methods, most of the analysis which we have carried out, either they are the relative or the comparative methods. So relative methods may you always draw a calibration curve. Okay, after doing the calibration curve only, you just use your unknown sample for the quantification purpose. Whereas in case of the comparative methods, the comparative methods again need a calibration, but in this calibration, while preparing the calibration curve, you need a matrix matching standard actually. For example, if you want to evaluate the concentration of the iron in any alloy samples, so then you have a standard sample of the metals only. So you cannot use the standard sample which is prepared from the soil or any vegetations or even any water samples there. So you should have a matrix matching standard when we are doing for the calibration for carrying out the calibration curve. The best example for this is the this XRFs and neutron activation analysis. So these are some of the technique which termed as a comparative comes under the comparative method. Then we had just just discussed about the solutions, and then stoichiometry. Stoichiometry means how you balance the equations actually. And in this thing, we have written that the state of the matter has been written in the parenthesis, while the coefficients or various coefficients in the equation has been used to balance the equations are there. And after having so, then we had discussed how the progress of the analytical chemistry. The analytical chemistry, we started with the gravimetry, then in case of gravimetry, we face certain problems. So those problems had been overcome by using the volumetric analysis. Volumetric analysis, both with the acid-base titration and the redox titrations are there. And then from the, we had moved for what is the problem which we are facing because of the, we cannot evaluate the small concentration, then we come with the various kind of a calorimetric calorimetric analysis actually, in which the analysis is done by using developing a color and then measuring the intensity of the color in that. Now, after discussing after discussing all those things, then we come the very important term, that is sampling. See, sampling is a very important part while we carrying out any kind of analysis, because if you are not done your proper sample, if you are not collect your proper samples, then you cannot do whatever best analysis you are there, whatever best analysis you are, and whatever best instrumentation you are having in your laboratory, you cannot end up with the results which is actually a required one. So that's how we discussed the importance of sampling. So in this, we have seen that both solid, liquid, and gases how to do the sampling. Now, what's this today lectures? Today lectures we have discussed about the sample storage and preservation, because after doing the sampling, one has to, because it's not always possible that immediately you can perform any analysis on site, or you will immediately do the analysis after bringing your samples. So most of the cases, 99% cases, you have to store the samples and then preservation. So while storing the sample today, we'll discuss, we must take utmost care that our annulate of interest should not be get lost during that storing process, or it should not get absorbed on the container walls and all those things. Then after having the sample storage, then sample preparations are there. See, sample preparations means, see, whatever the physical state you had collected the samples, it is not possible to analyze, it's not possible to evaluate the concentration of the analyte of interest in that physical state. So you have to prepare, you need a sample preparations. So that we will discuss, how to make various kind of sample preparations. And then after having the sample preparations, it is not necessary, in a one go you will do the analysis. So that is the separation of the analyte. So there are the various processes are there. For example, in case of ICPOS or AS or ICPMS, all the analyte can be done in a one sample itself. But it's not possible in always, it's only possible in some inorganic species are there. But if you are interested in some dyes or some pharmaceutical compounds are there, that is necessary to, separation of the analytes are there. Or sometimes because the concentration of the analytes is very, very small in that particular matrix. So you have to separate that analyte, you have to take out that analyte, that small concentration of the analyte from this major matrix. So that we'll also see. And then we'll discuss something of the chromatography techniques only. As I told you again and again, these are, just to give a glimpse of this thing, because all these lectures need a maybe about say 100 of lectures to carry out all these work. So sample storage purpose. So as I told you that there is a time gap between when the sample taken and actual analysis is being carried out. And during this process, there is a many ways to adulterate or contaminate actually by the foreign matters. And that particular that contamination may be maybe your element of interest only. For example, if you want in a water sample you want to do the analysis of the lead, and if you are not if you are not taken a proper care while storing it, so there is a chances that whatever lead present in the air that get absorbed during that period. So instead of getting X concentration, you will get a X+1 concentration. So there is additional amounts are there. And then this is also possible. See, while doing the analysis, the container, wall of the containers, sometimes they absorb various kind of heavy elements as well as some other compounds also. So that care also has to be taken that there should not be any loss of analyte either during the adsorption or absorptions on the containers. Okay, so then this is the, for example, liquid sample. For liquid sample, make sure that whatever bottle you are is kept with a tight stopper. And if your sample, see, once very important, suppose if you are carrying a liquid sample is there, so you must know the acidity, because the pH of your liquid sample will tell you what kind of a storage you have to use it. See, in case of a acidic in nature, that can be stored in a glass thing. Otherwise, in case of a basic thing, is always preferred that it should have a plastic container. Then solid samples. See, solid sample actually may, as it looks that it is easier to keep and have a large chance to be adulterated by foreign matter. But sometimes again, whatever your element of interest analyte, it will be get absorbed or adsorbed on the walls of the containers are there. Whereas in case of a gaseous samples, that is the sample, for example, this example I had given you the sulfur dioxide. Suppose you want to analyze the sulfur dioxide in the air. Since the sulfur dioxide in the air is not stable because of the reaction with the atmospheric oxygen, so you always say sulfur dioxide. So how to avoid it? Suppose if you are taken any air sample is there, you want to analyze the sulfur dioxide content. If it is not possible due to the on-site analysis, then it is always, to avoid the above reaction, you have to cool your sample at a 4 degrees centigrade. So this is just one of the examples there. But like that, there is others things also there. So one has to be very careful. Whatever the analysis you are going to, whatever the sample you have collected, you have to see that during that the time lapse between the collections and the measurement, you should not lose the identity of your analyte, or either nor lose the identity of the analyte, nor it will get lost or get contaminated by the outside atmosphere. So samples are preserved to prevent from decomposition, because there are certain cases that sample will decompose also. Okay, then precipitation of metals from if it is a water sample, there is chances if there is an increase in the pH, then there is a chances that it will get precipitated out. loss of water from a hygroscopic material. If your material is hygroscopic, then there is a chance that if it is not tightly, not kept in a airtight container, that you will loss of water from this hygroscopic material. And wherever we have to see, for example, if you are interested in doing the analysis of mercury or arsenic, then these are some of the volatile materials are there. So one has to be very careful while dealing any sample collection and looking for the volatile elements. Then once you have these samples are there, then you have to convert into laboratory-based samples. Laboratory-based samples means that you had collected 10 liters of the samples are there, okay? In case of liquid. So, but 10 liters of the sample we cannot analyze. Or in case of a solid sample, suppose you have taken a 1 kg or 10 kg of this sample is there and you just want to know. So, you have to convert these samples into a useful form which can be analyzed into laboratory. So, converting the sample to useful form means solid are usually, in case of solid, we usually ground it to suitable particle size. See, one thing is very important actually, if this is basically, important in case of the environmental samples. See, whenever we report any environmental samples that this particular soil contains this much amount of one particular metal ions are there. For example, copper in one particular region, this is the copper concentration in the soil sample. See, we always specify that it is in this kind, whether it's 100 micron particles or 200 micron particles are there. But as per the standard protocols are there, so either you have to use the 2000 microns, 200 microns or 2000 microns actually. So these are, one has to be very specific about the particle size also. And then see, most of the sample has to be reported in the dry form. For example, if you give the concentration that is milligram per gram of the soil samples or milligram per gram of any other thing, so it has to be on a dry basis only. And that also has to be written very clearly that you are reporting on a dry basis only. So dry the sample to get rid of the absorbed water. And then, it is always, very important for us to do the replicate analysis actually. So, but there are certain limitations are there in the replicate analysis. The replicate sample are always performed unless the quantity of the analyte or expense of the other factor provided. See, sometimes your concentration of the analyte itself is very small. Then you cannot perform the replicate analysis. Sometimes the cost of the analysis is very high. So in that case also we never, we try to avoid this replicate sample and be very specific and be very meticulous in submitting the results actually. What is the replicate samples? Replicate samples are a portion of a material of approximately the same size that is carried through an analytical procedure at the same time and the same way. And obtaining the replicate data on sample improve the quality of the results and provide a measure of their reliability. So actually means always, it is always desirable that one must do the replicate analysis because the single sample analysis, there is chances to have a, introductions of error because of the many reasons. Sometimes due to the processing, sometimes due to the personal error, or sometimes maybe because of the instrumental issues are there. So, but again, as I told you that the expense and the concentration of the analyte are the deciding factor actually, and then as well as the concentration are there, then depend on the your throughput of your laboratory also. So, how to prepare a solution in case of a solid samples are there? Okay, because most of the cases is not possible. For example, if you are doing XRM and all those things, then you can do the solid sample directly. But more than 70-80% times, it is not possible to do the solid sample alone. So we have to prepare a solution. You have to bring out your element of interest into a solution form. So for that, we have to you have to choose a solvent. And generally, what we prefer it the complete digestion. That is that's what is written there. the solvent is chosen that dissolve the whole sample without decomposing the analyte. So that is called as a complete digestions are there. And in this, or there are the various sources of errors are there basically. And once if any one of you are I think dealing with the chemistry, you should understand the kind of a problem or the kind of a issues are concerned when we are looking for the complete digestion of the samples are there. Of course, in case of a synthetic chemistry or if we got some synthetic material, that kind of problem is not there. See, once you are doing any synthesis, you know what kind of ingredient you are taken. So analysts are very careful in choosing the various kind of mixtures of the acids, which will completely dissolve your sample without disturbing the analyte actually. So that's are the sources of errors in the incomplete dissolution of the analyte, loss of analyte by volatilization, introduction of a analyte as a solvent, contamination, and contamination from the reactions of the solvent with the vessel's falls. So not only, see, this is also very important thing. See, many of these things, if you are taking PTFE vessels, it's okay. But if you are taking any other kind of vessels, there is a chances that you may get in some element from the reaction between the solvent which you are or acid which you are using it and the container, the reaction between the solvent and the container of the whatever container you are using it. So those are the major source of errors are there. And this, actually, this is a very important part actually. Whenever you are looking for especially this is true for if you are looking any kind of a metalloids in a potable water systems. See, as such, the definition of the word potable water is that, see, I do not know whether how many people know. See, water contains, all three kind of physical states are there. See, there solids are there are gases are there. So even if you take a glass of a water, but in that glass of a water also there is so many solid particles are there. Okay, these solid particles you cannot see from the naked eye. For example, in our laboratory, we can have a process by which we are getting in that is called a nanofiltration. So we are going up to the 0.6 nanometers of the particles. We start with the two larger particles, say 44.1 microns to 0.6 nanometers. So we take the filtration at a various stage and then see the particular metal ions, how that metal ion distributed into various this particles. We started from 4.1. Basically, 540 Wattman paper is, I think, 2.1 or micron. Whereas this about the, I think 10,000, 5,000 NWL, that is nominal molecular weight, approximately 0.6 nanometers. This is how this, the distribution of metal ions are there in the water samples are there. So whenever you are taking any potable water sample, this sample have to filter to the 0.45 micron filter paper, and then only you do the analysis actually. Otherwise, and where again there is a sources of error is there, that is incomplete filtrations are there, and that your element of interest, this particular analyte will be solved on the filter paper which you are using. So one has to taken care of those aspects. While the sample preparations in case of solid samples, the solid sample can be bring into the solution form, and before doing the solution form, we have to carry out the actually, before discussing this, most of the time we are doing the analysis of the inorganic analyte actually. And whenever we are looking for any inorganic species in a complete matrix means it contains both the organic and the inorganic components. So before doing the inorganic part analysis, one of us has to destroy the organic portions. So otherwise, what happens? Whatever the acid you are going to use it, you are going to get a puffy type of precipitate because there is a nitrate, organonitrate preparation presence will be there, and because of that, you cannot dissolve your sample completely. So that's why before doing any inorganic analysis, you have to destroy the organic components of that particular matrix. And how it can be done? It can be done by using the dry ashing. See, in the dry ashing, whatever the organic portions are there, that will be, that will be all the organic compound will be converted into the carbon dioxide actually in this thing, because they are burned off. And there are certain compounds where 400, 500 degrees centigrade temperature is not enough. So they need a higher temperature there. But in general, most of the organic compound get destroyed at 400 to 550 degrees centigrade is there. So whenever you bring any sample which contain you want to analyze any inorganic material in that matrix, so you have to heat the sample. You have to keep in a muffled furnace and keep at a temperature of 400 to 500 degrees centigrade for a few hours, and then when all the organic compound will be converted into, they're burned off and converted to carbon dioxide, and then whatever the remaining portions are there that you can use the acids are there, then even the simple HNO3 treatment will bring your all element of interest into the solution form, because all the inorganic species will be getting extracted into the HNO3. Whereas some cases, if it is not possible to do this dry ashing, then there is a way of doing the wet ashing. What is that? In this also, we are destroying the organic matter, but not by just using the heat, because here we are using basically a composition of acid where it can be easily, you can evaporate, you can destroy your organic compound. And for this, a method for the decomposition of organic materials such as resins or fiber into an ash by treatment with a boiling oxidizing acid or mixture of acid. And the acid oxidizes organic matter to carbon dioxide, H2O, and other volatile compounds. In this thing, because when we give a mixture of this thing, so along with the HCl, HNO3, we put a hydrogen peroxide. Basically, we are producing more nascent oxygens, and that reaction will be vigorous, and all the your organic compound will be getting converted into carbon dioxide, and that your solution will be free from the organic compounds are there. Then in both these cases, we can do this process by using these microwave digestions. So this also we'll see in the the coming PowerPoints, what is the advantage of doing the microwave digestions are there. And there are certain last stage is that fusion, and that also you'll see in the coming PowerPoint, that how to perform the fusion and what are the pros and cons of using the fusion. Actually, fusion is always the last resource. This is how we perform this dry ashing. Okay. What are the procedures there? Just performed by waste sample in a crucible, heat in a muffled furnace, and then the residue dissolved in a suitable acid. And as I told you, typical this ashing temperature is about 450 to 550 degrees centigrade. And sometimes, we use magnesium nitrate because it will act as a catalyst, and you will accelerate the process ashing at. And the charring the sample to pure is preferred. Actually, sometimes, because once you keep the in a muffled furnace, which is which work in a closed atmosphere, so you charred your sample actually. So whatever the initial burnings are there, where the lot of black fumes comes, so those things can be done in the open one, and that's why the charring the sample prior to muffling furnace is preferred. And generally, charring is accomplished using the open flame. And for example, as I told you, some non-volatile materials for mercury, arsenic. So during if you are interested in this mercury, arsenic, and lead, then proper care has to be taken for while performing this kind of a this dry etching. In generally, when we had to look for the mercury, arsenic, and lead, then we prefer this microwave digestion, because then there is a almost negligible chance that these material will be escaped during the process of a sample preparations. Okay. Now, if suppose if your liquid sample are there, then in liquid sample also, before putting into muffled furnace, this sample has to be dry. once the sample is dry, then it will act as a solid sample only, and then you can keep in a buffer furnace, and then you use in a, once the sample is kept in buffer furnace, after that we can dissolve in this, some amount of acids and get your element of interest into the solution form. So these are the basically advantages of a dry etchings are there, the ability to decompose a large sample size, and then there's a less reagent requirements are there than compared to the wet etching, and the technique is relatively safe, and the ability to prepare a sample containing volatile combustion elements such as sulfur, fluorine, and chlorine. For this, we have used the Schrödinger oxygen flask combustion technique, which is very popular in this case. And the technique, of course, led itself to a mass productions. And these are the certain disadvantages. The loss due to retention to the etching container. Okay, because some of the element of interest will be get retained into the acid container, so one has to be very careful to take out the completely, because after the transfer of the ash, it has to, the container also has to wash with the acids. Then, as I told you, there are certain, in case of volatile element, there is a losses due to volatilization, and there are certain contamination from the etching container itself. Contamination from the muffle furnace is also possible. And the physical loss of a low density ashes, for example, if your ash is low density, then when you take out your sample from the furnace, that's some kind of a ash will be flight within the furnace when you are opening the door of the furnace actually. So these are the certain problems are there, and of course, this basically whenever we are using this doing a dry etching, it has to be done in a properly ventilated, because most of the time this muffled furnace had been kept in a fume mode only. If the fume modes are not available, then proper ventilation should be there, so that whatever the toxic gases are to release, they should not be in your area of working. This is how we perform these wet etchings. We are using hydrochloric nitric acid, and in case of silicates are there, then we use the HF, or in case of if organic matters are present, then we use the hydrogen peroxide along with the HCl HNO3. And this basically general principle of the wet etching. Usually use combination of acid as most of you must be aware of that aqua that is 1:3, that is 1 portion of HNO3 and 3 portion of a HCl, that we are talking about the concentrated HCl and HNO3. And in case of silicate matrix, HF is added. And see, one more thing I'll tell you, if you are looking for some of these sample which silicates, looking for some ceramics and ceramic samples, then one has to be complete digestion of the samples is even not possible with using the HF also. Then we use a certain amount of boric acid, and that's whatever the fine silicas are present are there, so we get solubilized, and of course hydrogen peroxide or perchloric acid also used for the organic to break the organic complexes, and a small amount of Estressable used with large volume of HNO3, that is sometimes, for example, there are certain cases where we had a small amount of Estressable also, and most of these digestion has been done in either in a glass beaker or PTFE lined vessels, and even platinum dish. And HNO3, most of the time HNO3 destroys the bulk of the material, but it does not hot enough to destroy the last traces. That's why you prepare a boiled out during digestion process, only H2SO4 remains, and that's the fuming sulfuric acid actually we set it to do the complete digestion of the samples. So there are advantages and disadvantages of the wet digestions. The disadvantages, advantages means superior in terms of rapidity. low level of temperature is maintained, because it's not that you have to go for a 400, 500 degree centigrade temperature. Because once you have this mixture, so about say 100 degree or 150 degree centigrade is quite good enough for destroying even silicate or even the organic matrix are there. And it's freedom for loss of retention, because the walls of the container are always having in contact with your acids. So there is a less chances that any of your element of interest get absorbed or absorbed on the container of the vessels are there. And what are the disadvantages are there? Because we are using many type of reagents are there. So there are chances that you are adding impurities, or maybe your element of interest of analyte also you are adding during this process actually. And then I think this you all may be aware this microwave digestions. Okay, see in case of a generally we when we do the conventional when we do the heating, we are conventional heating. So basically the solvent or whatever the acid you are using it has to heat in a conventional manners. But once you are using in a microwave digestion system where the energy is given to the each molecules of the solvents are there. So in that case, your whole process will be very rapid, and you will get whatever the reaction, whatever the boiling temperature you are going to achieve in a conventional way about 20 or 25 minutes can be achieved within 1 or 2 minutes actually. So that is the main advantage. That is in contrast to the microwave energy is transferred directly to all the molecules of the solution, and nearly simultaneously without heating the vessels, and the boiling temperature reaches throughout the entire solution very quickly. And again, this is the advantage that because being in a closed vessels, there is a very low, the chances of volatilization is very less in this when we are performing the microwave digestions are there. See, as I told you, this is the last resource. Actually, generally chemists avoid the fusion. Why the fusion has to be avoided? Because it's a very time-consuming as well as the expensive one also. And then because ultimately you are bringing your analyte into a solution, but in bringing the analyte into solution, you are adding a lot of salts are there. See, basically, generally, one of the major flux is the sodium hydroxide and sodium carbonate, and sometimes peroxide, sodium peroxide also has been used. But in this whole process, you are bringing some, there's some lithium borate, there are many other fluxes are there, but all these fluxes, add lot of salt content into your solution. And many of the instrument, the tolerance of a salt contents is very limited one. So this is a major disadvantage while using the fusion, but sometimes there is no other way possible. So to bring out your analyte in the solution form, you need a fusion, and there we perform this fusion things. Okay, so fusion are considered to be, as I told you, last resort by trace analysts, because they're expensive and often not available actually. When high purity fluxes are not available because, as I told you, sodium hydroxide, sodium carbonate, they themselves will bring a lot of impurities into your solutions, and maybe your element of interest also will be present in those things if it is not a very high purity. If they are very high pure, then the cost will be very exponentially high. So they are expensive and not available, and high. They yield high solid content. As I told you, salt content actually. The salt content which always choke my nebulizer, because ultimately before putting this solution into any kind of instrumentation, there has to be put into a tiny droplet with the help of a nebulizer. So those nebulizers will be get choked when we have a very high salt content are there. And of course, same reason that spectral interference from the flux or crucible construction material must be considered. And the contaminations of the sample with the crucible construction element and impurity always may be there. And of course, they are the very labor intensive. So actually, if you have any queries, Anurag, how to see that how many people are there? Is there more chats? Chats. सबसे first option. अच्छा ऊपर second एक बार में how many people are there? Teacher लोग they are listening now. Yes. But if anybody has any questions up to now, see what we had done it, we had collected the samples, then we store the sample and then digest the samples. Okay. So if you have come across of any kind of a problem up to now, you tell me and then we can share, if it is possible for me to answer this, your query right now, I will answer it. Otherwise, I can ask some of the experts which is in that particular field. But I must come to know whether you are getting it or not. So it is always, good to have a interactive lecture actually. Any queries? Chat box I can. Okay. See, basically, now, see, this particularly, you don't take it as an environmental analytical chemistry. The basic difference, before going to various techniques, I want to tell you the main hurdle which an analytical chemist feel is to bring out your element of interest, because your element of interest is there in the major matrix actually, and how to avoid these major matrix actually. Okay, so the same thing is happening in this case of the environmental analytical chemistry also. Okay, so basically, see, analytical chemistry as such, see, when we are dealing with the normal analytical chemistry, we are dealing with most of the time with the synthetic sample actually. Synthetic sample means the sample which you have prepared into laboratory, or the sample which is prepared from the industry, where we know completely the process actually. What are the ingredients associated with that with the matrix or with the sample which is given, which is the handover to us. But in case of environmental samples, see environmental samples, all the samples are come from the nature. We do not know the constitution of the matter. We probably, that, for example, if soil is there, so about say 60% is the silicates are there, then some organic compounds are there, moistures are there, and some other elements. But otherwise, we is a basically unknown matrix actually to us. So this how this is the variation between the normal analytical chemistry and environmental analytical chemistry, which can be defined as the study of separation, identification, and quantification of the chemical components of environmental sample. And what is the difference between both of those things is that, see, is having the low concentration. Okay. So low concentration means basically we talk about the micrograms per gram, and sometimes with some of the emerging pollutant like the nanoparticles or some fullerenes or this thing. Then we are looking even up to the picogram per gram. So this is how, and to bring this nanogram or picogram of the material out of that major matrix is basically a challenge for the analytical chemist. And then during that process, he has to taken care, as I told you, that nothing to be added externally, nothing to be come out from the various vessels. Nothing should be lost during the time lapse between the collection and then storage of the samples are there. Okay, so just skip because these are not of basically this, whenever I give my lecture in on the environmental scientists, there I used to discuss these the important points are there. So basically, I want to come to this separation portions. See, as I told you, this is a big challenge for us to bring out a small amount of a matrix, actually, a small amount of analyte into a larger matrix, actually. And for this, we have to use the various kind of, techniques are there. And what are the major consider when we are looking for any technique, what are the considerations are there? We look that it should be very selective to that particular analyte, and then definitely to after getting it separated, we have to detect it also. So we should have a good detection limit. So selectivity and detection limit are the major criteria for choosing the any kind of going for any kind of equipments are there. And sometimes, whenever the concentration is very low, we are looking for a methods why we can do the pre-concentrations. And the best example of this pre-concentration is, yes, for example, we are given a 10 liters of waters, and it says that somebody say that it's only, 10 ppb of lead is present in the whole of this 10-liter water. Then what is the best way that you evaporate it completely and pre-concentrate it just by using this evaporation? The other way is that you look for any selective material. Okay, you look for some selective adsorbent which you put into the 10 liters of water, which will be selectively absorb the lead from the 10 liters of water. So this is two way of doing the pre-concentrations are there. One is the conventional way, other way you can take the help of the chemistry to pre-concentrate your samples are there. So various what are the separation methods are there? So one is the first is solvent extractions, then ion exchange and chromatography. So we will see one by one how we can pre-concentrate this, how we can separate the aromatic the solvent extractions. See how the solvent extraction actually, I think most of you might have considered in your BSc or BSc if you have done any, subsidiary course also the chemistry, or maybe I think in case of some 12th class practical is not there actually. So solvent extraction, how to define it? The distribution is solvent extraction basically, as the name suggests. Basically in this we are using the two different solvents are there. So distribution of species between two phases, and one of them is usually aqueous and other is immiscible organic phase are there. So basically we are using both aqueous and as well as organic solvent in this, and that we call as a liquid extractions. And liquid extraction has been, they had been categorized on the basis of their partition coefficient actually. So partition coefficient is nothing but the distribution of the solute between the two phases. Okay, so how the K is defined, the K is the concentration of the solute in the second phase compared to the phase one. So this is how, and this distribution, this partition coefficient for various kind of solvents actually, it's already is well established in the literatures. One can take the help of those partition coefficient and then look for it for the separations of the analyte by using the solvent extractions. So in this, I just take the example of what we are doing in our laboratory, that we are doing the separations of the uranium actually. See, for this, we are using this organic phase, we are taking as a tributyl phosphate, whereas the aqueous is just a simple water with the acidic water, HNO3. And in this, after few extraction means almost 3 extraction, all the uranium, because all the uranium will go from the aqueous phase to the organic phase. So this is a basically a typical example how we separate the. See, here our aim is that we got some of the uranium sample. In that uranium sample, we have to determine the concentration of the various elements in that. Okay, since uranium is the major matrix, and if I using any kind of equipment, so all the interferences come because of this presence of the major matrix uranium. So I want that uranium should be completely removed from the samples. So how I proceed is I take this, I extract the whole uranium into tributyl phosphate, and whatever the iron is there, whatever the other elements are there, they are present in now this aqueous solution. So whatever the analysis, for example, in this case, we are using this indirectly covered plasma optical emission spectrometer for determining the concentration of various analytes. So all these emission spectra are now free from the uranium, and that's how I successfully remove or separate my trace elements from the major matrix of the uranium. And these are the certain example of various kind of common complexing agents are there, which we use for the various separation of the various metal ions that we call the major matrix. So the cuprophone, hydroxyquinoline, diazoxide, and brown crown plus. Then comes this ion exchange. Ion exchange, I think most of you are aware. So there is basically cation exchanger and anion exchanges, and there is a simple selectivity will come in this particular set. So basically, they are the reversible exchange of ions between a solid and a liquid in a contact with each other. And then there is both, cation exchanges are there and the anion exchanges are there, and they are all these, famous example of the styrene divinyl resin, and how is prepared by mixing the styrene and divinyl benzene. Okay, so these are basically what kind of various anion exchangers are there. See, anion exchanger, maybe the quaternary ammonium groups are there. Alkyl amines also will come in the category. Then hydroxyl alkyl amines and alkyl amines with the acrylate tri-cross linking are there. And whereas in case of a cation exchanger, so there may be the moieties, so which is exchanging, they are the sulfonate or a carboxylates are there. And these are the various kind of substrate by which we are preparing this resin there, that is polystyrene and divinyl benzene, polymeth, acrylate, polyalcohol, and hydroxyl ethyl methyl acrylates. And this is how, again, this, the selectivity coefficient, how the selectivity coefficient has been evaluated. So, basically, the simple equation that, if you're using the cation exchange are there or the anion exchange are there, you have to write an equation for that thing. And then the distributions can be evaluated by evaluating this selectivity coefficients. This is termed as a K here. Okay, and what are the factors which affect this selectivity coefficient? For a given resin type ion selectivity is a function of ionic charge and hydrated radius and functional group ion chemical interactions. Okay, so it's a function of the ionic charge and hydrated radius and then functional group ion chemical interactions. And in most cases, the higher the ionic charge, the higher the affinity. And similarly, if the smaller the hydrated radius of the ions, the greater the affinity. Basically, the more ionic potentials are there, then it will lead to better affinity actually. It can be done by either the smaller hydrated radius or maybe because of the higher ionic charge, which will both bring the better affinity. Now, coming to this chromatography, so just I given an introduction of both these solvent extractions as well as the ion exchange. Again, I request you please, because as the Anurag, ऊपर चैट पे जाने का. Uh, so again, I request you, please, if any queries are there, please come forward actually. And don't feel bored yourself. At least you have to entertain yourself also by asking some questions. Okay. Surgeon Singh. For method validation purpose, my CRM of groundwater does not contain any element of interest. Can I present other element recovery since matrix of the sample CRM is same? No, Dujan, actually, this is a common practice. What we are doing is, for example, if you are doing a reference material, okay, that reference. Suppose your reference material, groundwater, you are having a groundwater reference material in your lab, and you are doing the analysis of, say, about cadmium, and cadmium is not present in your element of interest. It contains iron, cobalt, nickel, chromium, but cadmium is not there. So what you can do it, you can add you can spike the sample with the cadmium. At least then you have a matrix matching standard. That's we call as a in-house reference material. Okay, then it will be termed as a not even reference material. That's called an in-house reference material because your matrix now will be same only. Understand? So you are doing the analysis of cadmium in the groundwater samples, and that too in the same matrix. Why this is important? Because see, either what are the problems, what is the need of getting this reference material actually means? See, reference material is validating your processing. See, while doing the processing, you are not add your cadmium. It will validate your instrument also because of the instrument, because of the some calibrations issues or due to some other reason, you are not either getting an enhanced signal or not getting a negative signal. Negative signal, your concentration would be less also. So these are the some of these things you are avoiding by using the same matrix actually. So this there's no harm. You can spike your groundwater with the cadmium and then do the analysis. Okay, I clear to you? Sajan, clear to you? Okay. Anybody else? No. Okay. Now we are coming to this next technique that is we call it chromatography. See, chromatography is a technique here. Not only we do the separation, we are doing the quantification also. So it's basically a technique where we are doing both the qualitative and the quantitative analysis. So what is chromatography? Chromatography is defined as a procedure by which solutes are separated by a dynamic differential migration process in a system consisting of two or more phases, one of which move continuously in a given direction and in which the individual substance exhibit different mobility by regions of differences in adsorption, partitions, solubilities, vapor pressures, molecular size, or ionic charge density. So you can see that what are the phenomena by which your chromatography differentiate adsorptions, partitions, solubility, vapor pressures, molecular size, or ionic charge density. In the coming PowerPoint, we can see one or two all these cases actually, how they vary from one chromatography technique to the other one. So basically, when we talk about the chromatography, so the basic terminology in the chromatography is this, mobile phase, the phase that travels through the column, that is gas or liquid transport samples through the column. Then a stationary phase, immiscible that can be immiscible solid, or a liquid that fixed in places in the column or on the solid support and retain annulate within the column itself. Then we also come across the band or zone. What is the band of zone? A area across which analyte is distributed on column or zone of a different analyte gradually separate as the band progress down. Okay, so this is a column progress, sample, mobile phase, stationary phase, detection method, and chromatogram. So we see one by one all those things, you know. See, basically the classification of these methods are, there are two way by which we can classify these various schemes are there. One is the mobile phase and other one is the attractive forces. So how they varies from each to one from one another. See, one mobile phase. The mobile phase is a gas, then we call it the gas chromatography. Then the mobile phase is a liquid. Basically, that liquid can be a water, and in case of a organic solvent, it can be a organic solvent also, and it will be a supercritical fluid also. So, what is the supercritical fluids are there? Supercritical fluid is any substance at a temperatures and a pressure above its critical point where distinct liquid and a gas phases do not exist, and but below the pressure and liquid to compress it into a solid. And what are the example for these things? The supercritical fluid chromatography is a form of normal phase chromatography. It's a normal phase of chromatography, and that uses supercritical fluid. What are the example of those things? Such as carbon dioxide. Anurag, there are some questions are there. तो ये ऊपर क्यों नहीं जाते? ये थोड़ा ये क्या बोलते हैं उसको, पैंट है। अच्छा, मेरे को लगा बीच में है। ओके, ठीक, कोई ज्वाइन किया होगा सब। Okay, then this gas chromatography has been termed as a gas solid or a gas liquid. And it will, what is the stationary phase? The stationary phase is either a solid adsorbent termed as a gas solid chromatography, or a liquid on an inert support that will be termed as a gas liquid chromatography. See, what is the major characteristic of the gas chromatography? Gas chromatography is the only technique chromatography that does not utilize the mobile phase for interacting with the analyte. See, in this particular technique, in the gas chromatography, there is no interaction between the analyte and the mobile phase. So always what we choose is the mobile phase, which does not interact with the this analyte actually. That's how we will see also some of the example in this case. Okay, then the classification based on the mobile phase, that is a liquid chromatography. That liquid chromatography is a column, and in which this work on the principle of the gravity flow. Then high performance nothing but the pressure flow, because this is basically a HPLC means high pressure liquid chromatography. Then we will have an example of categorization of a thin layer, which is basically based on the adsorption process. Okay, then classification based on these attractive forces में adsorptions, ion exchange, partitions, and the size exclusion. I see the when we consider about the adsorption chromatography. Adsorption chromatography, see, as I told you, each chromatography will have its own 2 or 3 lecture process. So just I am giving the idea what for each chromatography technique, so that at least in whenever you have any kind of a such kind of a problems are with you, so you can how to resolve that problem or whom to approach to get your sample done. So adsorption chromatography is nothing but is based on the principle that same solid substance which are known as adsorbent have the power to hold molecule at their surface. This is very important here. Principle that some solid substance which are known as adsorbent have the power to hold molecule at their surface, and this holding force is due to weak non-ionic attractive forces like van der Waals or hydrogen bonding, and which only occur at the absorption batch only. Okay, so this is separation. So as I told you, the separation based on the absorption on the surface of the solid, that is stationary phase, and the normal phase is like separations. And in this, the non-polar mobile phase are there, and for polar non-ionic, compounds. This is how we the utilization of this adsorption chromatographies. Then in the partition chromatography, here the solutes are separated based on their partition between a liquid phase and a liquid stationary phase coated on a solid support. And in the case of it, because it can be done in both the normal phase chromatography or the reverse phase chromatography. In the normal phase, analyte is non-polar organic, and the stationary phase is more polar than the mobile phase. Whereas in the reverse phase, analyte is a polar organic, and the stationary phase is a less polar than the mobile phase. And for example of this type of a partition chromatography is the thin layer chromatography, paper chromatography, and how these various phases are separated in this particular case. That's what is shown here in this. Then comes this ionic chromatography. This basically use ionic stationary phase, and the ion separated on the basis of the tendency to displace counter ion adsorb on the stationary phase. And again, it depends on the charge, that is the hydrated radius, and then the solubility basically, and used for the analysis of main purpose of main utilization of this in case of amino acids and its base pair and its base pairs. And ionic stationary phase is used for the cationic separations, and cationic stationary phase is used for the ionic separations. And for this can be used also for the various kind of the ionic compounds. So this, how the utilization of the ionic chromatography. And the size exclusion chromatography, as the word says, the size exclusion chromatography. See here, basically, separation based on is a result of trapping of molecules in the pores of packing material. Various pores are there. There are a few microns are there. There are sometimes, varies from few nanometer to few microns pores are there. And that's how we, in which the very large molecule can't get trapped into this one, and they remain undetected and unretained, they will come out fast. And very small molecules get hold up in those pores for a long time until as we use another mobile phase to remove it then, and they will retain for a longer time. And stationary phase is basically is a porous material. Actually, there are different kind of methyl meth acrylates. There's, I don't remember exactly the pore size in that phase, but there are a few microns actually. And basically, when if anybody is working with the humic acids or a large molecular, when you want to separate the large molecular weights compounds from the for example solution, in our case we are using humic and fulvic acid separation actually, therefore which we are using this kind of a resin actually, because if you remember, I don't know whether humic acids are a very high molecular weights, soluble organic compounds are there in our aquatic systems. So these are the various types of chromatography. The liquid chromatography, separate liquid samples with a liquid solvent mobile phase and a column composed of a solid base stationary phase. Gas chromatography, separate vaporized sample with a carrier gas and a column composed of a liquid of a solid beads as a stationary phase. Paper chromatography, separate dried liquid sample with a liquid solvent, there is a mobile phase and a paper strips, that is termed as stationary phase. And the thin layer chromatography, separate dry liquid sample with a liquid solvent and a glass plate covered with a thin layer of aluminum or silica that becomes stationary phase. So in case of paper chromatography, the stationary phase is a filter paper, so a cellulose. And in case of a thin layer chromatography, it can be a silica gel, alumina, or a polyamides. Whereas in case of a gas chromatography, the stationary phase is cycline, apigen, or carbovex M. And in case of high pressure liquid chromatography, it can be C8 or C18s columns are there, or lycosols or silicons. Whereas mobile phase paper chromatography, we have a air or alcohols. In case of thin layer chromatography, maybe hexane, petroleum ethers or alcohols. In case of gas chromatography, if you remember the word which I use, the gas chromatography is the only technique where your mobile phase does not interact with your analyte. So you can see that this mobile phase is either helium, argon, or nitrogen. It does not interact with your analytes are there. Then high performance liquid chromatography, the mobile phase can be cyclohexane, anhexane, carbon tetrachloride, ethanols, or methanol, or even air also. So this is some, in brief about the paper chromatography. See, a chromatographic analytical separation technique for a complex mixtures involving the progressive adsorptions of the dissolved component into a special grade of a paper. And the principle is that certain solvents are used to separate a mixtures, for example, water or alcohol. With a capillary action, the solvent will move up to a filter paper, and movement of a solvent will bring together components that are separated from the mixtures. And every component that is separated will move at a different velocity. Here, the most important thing, what I want to introduce the RF factor actually. That is called a retention factor. And this is how, once is evaluate the retention factor. The retention factors or RF is defined as the distance traveled by the compound divided by the distance traveled by the solvent. Okay, so basically this once you know this retention factors, and it's not only it's true for most of the chromatographic things are there. So that's how the importance of this retention factor. See, until you ask something to me, because for me I am doing these things in and out actually. Very difficult to until because we are not a very professional teachers. Professional teacher because basically we are working in the laboratories only most of the time. So until some of the question you ask me, I do not know what kind of problem you are facing it, whether you are understanding or not. If there are any kind, because if you interact with me, then it's a very easier for me also to get an idea that whatever I'm telling to you, you are getting a part of it or not. No questions. Okay, then this is the instrumentation of the HPLC. So basically, there is a reservoir for okay. Before pumping, before putting into pump, you have two different mobile phases. The reservoirs are there. They will mix it and then pump it, and it goes to the column and detectors. There are certain wastes are there. Okay, whatever coming out of the waste, and then detector is giving you signals, and that's how we generate the this HPLC charts. And what kind of detectors are possible in case of HPLC? We have a refractive index, and there the sensitivity is about the 100 nanograms per ml. Whereas in conductometry, it's still better, 100 nanograms per ml. UV spectrometers, it's about say 10 nanograms per ml. Mass spectrometry, because you can attach your SPL, any kind of a detector with your HPLC. So once the HPLC will separate your, that we will see in the hypnotic technique also. The HPLC main job is to do these separations only, and then the other parts will be done by the detectors only. So by putting the various kind of detectors, we are getting a quantification at a various levels actually. So you can know with the help of a fluorescence detector, if you are having a fluorescence one, then your detection limit is 0.001 nanogram per ml. It is basically 1 picogram per ml. So you know how sensitive this technique is there. And this is how this chromogram looks like. And as it can be used both for the qualitative as well as the quantitative things. Qualitative means you can separate the mixture, and quantity means you can know this the concentration of that particular compounds are there. So it can be used both for the purification purpose. In purification purpose means you are just separating the compound, and then you can do the identifications of various compounds are there. So we will see that some of the example how we can utilize this HPLC in various of our day-to-day life. See, as I told you, any of the instrumentation does not know what, see, for example, the peak heights are there. If you don't calibrate it, it does not understand at the which, what particular concentration, what heights are there. So one has to be, do the calibration. So this is how the calibration is generated, calibration curve is generated. And then this concentration versus peak heights are there. And then you put in one your unknown samples are there. Then you will get the idea of, then you can do the quantification of the samples also. The another example is this gas chromatography. So this is how this, this instrumentation in the GCs looks like. Okay, so once you go there, your all the columns in the oven is there, and where you are using again the various kind of detector. And here I just give an example of one. This is flame FID detector, which is flame ionization detector. What is happening in case of flame ionization detectors, which you are generating the chromatograms are there. So there are the various GC columns are there. It can be a packed column, or they say open tubular columns are there, and each having its own advantages and disadvantages are there. There are various reasons are there to use both kind of columns are there. So this is that flame ionization detectors that is called as FID, and in this how we are generating this formal ions, which is basically coming to this and then gives us a current. So what is happening here? The flame ionization detectors, the organic solutes are burnt in a flame, producing the CH radicals, and eventually these CH radicals will lead to these formal ions, and then these formal ions will be collected cathode and produce current as the response actually. So the various concentrations we are getting a various amounts of formal ions, and accordingly the current, the various quantity, the current quantity will be generated actually. So these are the various applications of this gas chromatography, as told you, both for this qualitative and quantitative purpose. And then see, this mostly used for the identification of non-volatile. It is used for the identification of non-volatile materials like plastics, natural and synthetic polymers, and some microbiological materials. And how this separation is based on, this is based on the fingerprint chromatogram for the sample with results from the thermal dissociation and fragmentations, and various aspects of this aspects of the gas chromatography applications. The food analysis. See, analysis of food is concerned with confirm the presence of determination of quantity of the analyte like lipids, proteins, carbohydrate, preservatives, flavors, colorants, and also vitamins, steroids, and pesticides. So all those things can be resolved by using this, can be done by using the gas chromatography. Again, in this case also, you need a various kind of standard reference materials to confirm whatever the analysis you are doing, it is a correct one or not. Then drug analysis also, this is widely applied for identification of the active components and possible impurities as well as the various metabolites. Yes, the environmental contaminants like DDT or PCB. PCB is nothing but the polychlorinated biphenyls. Whether they are present in the environment, actually when they are in a very small, their small concentration also still very hazardous. So one has to be very careful. And in this can be done by using this GC. And GC means high sensitivity, high separations power is mostly, these are the major advantages while doing the environmental sample analysis. Forensic sample also can be done by using this GC. Because forensic sample, this major hurdle is that very low quantity of the samples are there. Okay. So the sample component is very low, and that's how the GC is compared to the other technique where the sample requirement is high. Then GC is useful. Same work can be done with a high sensitivity and separation coefficient by using the GC, though the sample content is very small. See this because still whenever we look over the paper chromatography, I think paper chromatography all of us has done in, I think, in our 12th class also. So still there is use for the separation of ink dyes, to compare ink dye using any company. Food coloring, to differentiate coloring agent using the food product. And then various botanies and herbalists also used to isolate plant pigments from the roots and leaves. Okay, now again, I am asking if there is any queries are there, please come forward. How many people are there who are listening?
7 on YouTube.
Only 7, no? These are the things, no?
These are my best.
They can listen and they can answer also.
Yes.
Can you just put it there so that I can bring? At least some people will be interacting, then it's very easy for me to. क्या वो सर्जन सिंह गया जल्दी था जिसको लगता है एक्चुअली मैं क्लासरूम में लेक्चर देना बहुत अच्छा लगता है बिकॉज they can also interact and they